Good morning, students. Today we are going to discuss our first chapter, that is Introduction to Coordination Chemistry. The compounds containing coordinate bonds with a complex structure are called as coordination compound. Coordination compounds are the special class of compounds which contains a central metal atom or ion surrounded by a cluster of ions or molecules, that is ligands. The study of such coordination compounds is known as coordination chemistry. The historical development of the coordination chemistry studied in three different eras. First, study from 18th century up to 1893. Second, the Wernerian era 1893 to 1940, and third one is the modern developing era, which is from 1940 onwards. The discovery of a first coordination compound was not exactly noted, but an artist color, that is Persian blue, Caesian Epicyan twice, Epicyan thrice, was recorded in 1704. It was obtained accidentally by a color maker Deichbach in Berlin. At that time, he prepared Persian blue by heating animal waste and sodium carbonate in iron pot. Some of the earlier report of coordination compounds are, that is, in 1753, potassium hexacyanoferrate second by Macquer from Persian blue and alkali was reported. Second, in 1798, hexaamine cobalt third chloride by Tassart. It is prepared from cobalt chloride and liquid ammonia. In between 1800 to 1850, large number of coordination compounds were prepared that are particularly studied by different scientists and put forth several theories to explain the nature and structure of coordination compounds. Some of them are Graham in 1778, Berzelius in 1878, Werner in 1893. Double salt and coordination compounds. At the beginning, large number of inorganic compounds were prepared that are double salt or molecular compounds, that are KCl MgCl2 6H2O, which is called as carnallite, ApSO4 NH4 twice SO4 6H2O, ferrous ammonium sulfate FAS, K2SO4 Al2SO4 thrice 24H2O, potassium alum. These double salts retain their identity for all its ion in aqueous solution. At the same time, there is the preparation of coordination compounds. That coordination compounds are different from these double salts. The compounds like K4-APCN6, which are called coordination complex, this complex lose their identity, individual identity of ions, that is Ap2 plus and Cn minus in aqueous solution, and give the test for only K plus and the complex ion ApCN6. Here we are going to see the difference between the double salt and coordination compound. See, Double salt exists only in crystalline form, while coordination compound exists in crystalline as well as solution state. Double salt in double salt, the constituent ions do not lose their identity in solution, while coordination compound, the constituent ions lose their individual identity in solution. Double salt, all ions can be detected even in solution, while in coordination compound, all constituent ions cannot be detected. In double salt, complex ion is absent, while in coordination compound, complex ion is present. Example of double salt: carnallite, KCl, MgCl2, 6H2O, and FAS, ferrous ammonium sulfate, FeSO4, NH4 twice, SO4, 6H2O, while the coordination compounds like K3, FeCN6, CO, NH3, 6, square bracket complete, CN3. While studying coordination chemistry, some important terms which are involved in coordination chemistry are very important. So here we discuss that terms which are involved in coordination chemistry. First, coordination compound or coordination complex. What is meant by coordination compound? Coordination compounds are the special class of compound which contains a central metal atom or ion surrounded by a cluster of ions or molecules which are called as ligands. There is coordination bond between the central metal atom and ligand molecules. In coordination compound, usual valency consideration of central metal atom or ion exceeds, that is, number of bonds formed by the central atom or ion is greater than the usual expected valency of that atom. For example, in CONH36Cl3, the usual valency of cobalt is +3, but it forms the 6 bonds with 6 NH3 molecules, that is ligands. Similarly, in K3FeCN6, the usual valency of Fe is +3, but it forms 6 bonds with 6 Cn- ions or ligands. Coordination compounds may be cationic or anionic or neutral. It depends upon how it will be get ionized. The first, CONH363 plus, it have the positive charge, so it is cationic compound. Second, CONH363 minus, it have negative charge, so anionic compound. And CONH3 thrice CN3, it does not have any charge, so it is the neutral compound. Second important term is the complex ion, a charged species in which metal atom or ion is directly attached to the central metal atom or ion. It indicate the enclosed in a square bracket. For example, CONH363 plus and FeNH363 plus. Next important term, that is central metal atom. A metal atom present in a neutral oxidation state in coordination compound to which neutral ligands are attached. For example, in NiCO4, Ni is zero oxidation state while CO have the zero charge. And second, FeCO5, here also Fe is in zero oxidation state and ligand carbon monoxide CO does not have any charge. Next term, central metal ion. A metal ion present in its charge in coordination compound to which neutral or negative ligands are attached. For example, in K3FeCN6, Fe3 plus is central metal ion, and in CONH36Cl3, CO3 plus is a metal ion. Next, coordination number. The coordination number of the compound is very important. The number of ligands or coordinated atoms, ions or molecules which are directly attached to the central atom or ion is called as coordination number of that metal atom or ion in that complex. The most common coordination number shown by the metals are 2, 3, 4 and 6. A metal atom or ion may show different coordination number in different complexes. For example, coordination number of CO3 plus in CONH36 Cl3 is 3. In CuNH36 square bracket complete 2 plus, it have the coordination number 6. Coordination number of some common metal ions in their complexes are shown here. See, CuNH3 twice, metal ion in Cu plus 1 and coordination number is 2. AgCN2 1 minus, metal ion is Ag plus, coordination number is 2. AgNH32 1 plus, metal ion is Ag plus, coordination number is 2. CuNH34 2 plus, metal ion is copper 2 plus, coordination number is 4. NiCl4 2 minus, metal ion is Ni2 plus, coordination number is 4. Similarly, there is FeCO5 Fe0 and coordination number is 5. In MnCO5, Mn in zero oxidation state, coordination number is 5. PtNH36 4 plus, Pt4 plus is the metal ion and coordination number is the 6. And thus we have the cobalt complex, nickel complex, they can show. Next we are going to see ligand and their types. Any atom, molecule or ion which can donate pair of electron to central metal atom or ion is called as ligand. It is also called as coordinating group. In a ligand, a particular atom can donate electron pair. That atom is called donor atom or donor site or coordinating site. A ligand may contain one or more donor atom. That is, it can form one or more coordinate bond with central metal atom in coordination compound. Ligand may be neutral, negative or positively charged atom, ion or molecule. Negative ligands, for example, F minus, Cl minus, Br minus, I minus, Cn minus, NO2 minus, C2O4 2 minus. Neutral ligands, for example, NH3, water molecule H2O, carbon monoxide CO, ethylene diamine NH2, CH2, CH2, NH2. And a positive ligand, for example, N2H2, NH3, NH2, NH3 plus. Types of ligands. Depending on number of donor atoms or coordinating sites in ligand, they are classified as monodentate ligand, bidentate ligand, and polydentate ligand. These types of ligands may be negative, neutral, or positive, atom, ion, or molecules. First, monodentate ligand. This type of ligand contains only one donor atom, that is only one coordinating site. That is, form only one coordinate bond with the central metal atom. That are F minus, Cl minus, Br minus, I minus, Cn minus, NO2 minus, H2O, CO, NH3, etc. Second, bidentate ligand. This type of ligand contains two donor atoms, that is, it can form two coordinate bond with central metal atom or ion by two separate donor sites. For example, ethylene diamine NH2, CH2, CH2, NH2 and 2,2-dipyridyl or C2O4 2 minus, etc. And third one is the polyrendered ligands. Polydentate ligands means they can form more than two coordinate bond with the central metal atom. This type of ligand contains more than 2 donor atoms, that is, it contains 3, 4, 5, 6 donor atoms. That polyrendered ligands are identified as per their capacity to form the bonds with the central metal atom or number of donor atoms. If it contains 3 donor atoms, then it is called as tridentate ligand. If it contains 4 donor atoms, it is called quadradentate ligand. If it contains 5 donor atoms, it is called pentadentate ligand. And if it contains 6 donor atoms, it is called hexadentate ligand, and so on. Examples of various types of ligands. First, we see the unidentate or monodentate ligand. For example, water, its symbol is ACO, H2O. Second, ammonia, which is called as amine, NH3. Pyridine, represented as PY. And bidentate ligand, ethylene diamine, represented as EN, NH2, CH2, CH2, NH2. Second bidentate ligand 2,2-dipyridyl, it is denoted as DIPY. Bidentate ligand, another one is 1,10-phenanthroline, which is represented as PHEN. Glycinato ligand, represented as GLY. Its structure is here, that is NH2CH2 COO-. Another bidentate ligand, acetyl acetonato, represented as ACAC, that is CHO CH3 COCH3. Bidentate ligand, another one is, that is dimethyl glycosamine, which is represented as DMG. Next bidentate ligand, oxalato, that is C2O4 2-. Then another types of the polydentate ligands, that are tridentate ligands, diethylene triamine diene, 2,2-terpyridine. Tetradentate ligands, triethylene tetramine. Pentadentate ligands, ethylene diamine triacetate. And last, that is hexadentate ligands, which is the ethylene diamine tetraacetato, EDTA. Here it have the 6 coordinating sites. It will be bind to the metal atom from 6 sides, and thus it is the hexadentate ligand. Surprisingly, monodentate ligand may coordinate with 2 or more metal atoms to form a bridge bond between them. A ligand which form bridge bond between 2 or more metal atoms in a complex is known as bridging ligand, and complex is termed as bridging complex. See the example of this complex. In this bridging complex, NH2 and NO2 ligands are bridging ligands. Polydentate ligands may act as a bridging ligand. Metal chelate and metal complexes. As polydentate ligands have 2 or more donor atoms, they can coordinate the same metal atom by more coordinating sites. Such ligand is called as chelating ligand and chelating complex, while the monodentate ligands can form a metal complex. For example, it is MNH2CH2CH2 thrice 3+. Here M is equal to nickel or cobalt. Coordination compound with the monodentate ligand is called as coordination complex, which coordinated with the with bidentate or polydentate ligands can form the chelate. We are going to see the difference between the metal complex and metal chelate. We know that metal complex is the coordination compound with monodentate ligands only, while metal chelate is the coordination compound with the bidentate or polydentate ligands. Monodentate ligand can form the complexes. See the metal complex. Monodentate ligands with metal forms the metal complex. Such ligands are called as complexing agent, while bidentate or polydentate ligands with the metal forms the metal chelate. Such ligands are called as chelating agents. It is less stable, that is metal complex is less stable than chelate compound, that is it is moderate stable, while the metal chelate is more stable than the complex, that is it have high stability. Heterocyclic ring is not formed in metal complex, for example non-cyclic compounds, while heterocyclic ring is always formed in metal chelate, that is cyclic compounds. Example of metal complex CONH363 plus. See its structure. An example of the metal chelate is COEN thrice 3 plus. See its structure. Now we are going to see the charge on complex ion. The charge on the complex ion is algebraic sum of the charges carried out by central metal ion and the ligands attached to it. The charge on complex ion depends on the nature and number of coordinating ligands or groups attached to the central metal atom or ion. The charge on the complex ion may be positive or negative. For example, CONH35 Cl 2 plus FeCl6 3 minus PtNH34 2 plus. The complex ion CONH35 Cl 2 plus have a net charge 2 plus. It is algebraic sum of charges of metal ion and ligands. This plus 2 charge of the complex is calculated by the summation of plus 3 charge of cobalt, 0 charge of ammonia molecule or ligand, and minus 1 charge of chlorine ion. That is plus 3 plus 0 plus in bracket minus 1 is equal to plus 2. The complex FeCN63 minus have minus 3 charge. See the summation of the charges, plus 3 minus 6 is equal to minus 3. Similarly, PtNH34 2 plus have plus 2 charge and it is calculated by the summation, that is plus 2 plus 0 is equal to plus 2. Thus plus 2 is the charge of this platinum complex. See some complexes, their complex ion, what is the charge on metal ion and charge on the ligands. We are considering the total calculated charge also. CONH36Cl3, here charge on the complex is plus 3, ammonia has 0 charge, and summation of the charges is plus 3 plus 0 into 4 is equal to plus 3. PtNH3 thrice Cl square bracket complete Cl, PtNH, here it have the plus 2 charge, NH3 have 0 charge, Cl have minus 1 charge, and summation is the plus 2 plus 0 minus 1 is equal to plus 1. K4FeCN6, it have the plus 2 charge, Cn have minus 1 charge, so charge summation is plus 2 minus 6 is equal to minus 4. AgNH32 SO4, it have the plus 2 charge, so charge summation is the plus 2 minus 0 is equal to plus 2. So thus we are going to calculate the charges of the compounds. Calculation of oxidation state of central metal ion or atom. When we are going to see the coordination compound, the charge on the metal ion or the oxidation state of the metal ion is very important. And that oxidation state is important to consider its number of electrons and the other properties. So this oxidation state is very important, and we are going to calculate that oxidation state from the charges of the metal atom and the charges of the ligand. The charge on the central metal atom or ion in a coordination compound is known as oxidation number or oxidation state of that metal, ion or atom. Oxidation state is the characteristic of central metal, atom or ion in a coordination compound. Oxidation number or oxidation state is the similar. The oxidation state of the central metal, ion or atom is shown in Roman numericals as 1, 2, 3 or 0. For example, in FeCN6 3-, the number of ligands, that is coordination number, is equal to 6. Charge on each Cn- is -1, and oxidation state of metal is X. Consider it is X. It is unknown. How we can calculate? We know that the charge on the complex is the summation of the charges of the metal atom and charges of the ligands. So according to that formula, we can write X plus -1 into 6 is equal to charge on the complex. So it is X minus 6 is equal to -3. By the mathematical calculation, X is equal to -3 plus 6. So X is equal to +3. The oxidation state of Fe is equal to X is equal to +3. See the second compound. We know that the charge on this complex ion is -4, and this charge, how it is calculated? It is the summation of the charge of the Fe and 6 cyanide ligands, and charge of Fe is nothing but the oxidation state. So this charge is calculated as X plus -1 into 6 is equal to charge on the complex. See, X minus 6 is equal to -4. Now therefore mathematically X is equal to -4 plus 6, that is X is equal to +2. So here +2 is the oxidation state of Fe. See the next compound, MnCl4 2-. Again here charge is -2. We know that -2 is the charge which is calculated by the summation of the charge of the Mn plus charge of the 4Cl-, and the charge on Mn plus is the oxidation state. So here we have the equation, that is X plus -1 into 4 is equal to charge on the complex, that is X minus 4 is equal to -2. Therefore X is equal to -2 plus 4, that is X is equal to +2. That means +2 is the oxidation state of Mn in this complex. Next example, COF6 3-. Here 3- is the charge on the complex. It is calculated as, consider the charge of the CO is X, and so we have the equation X plus -1 into 6 is equal to charge on the complex. X minus 6 is equal to -3. X is equal to -3 plus 6, that is X is equal to +3, and the oxidation state of CO is equal to X, it is +3. Next, NiCO4. Here this complex does not have any charge. We know that CO, carbon monoxide, have the charge 0, and so the charge on the complex is the summation of the charge of the metal atom and charge of the ligand. So X minus 0 is equal to 0. Therefore X is equal to 0. That is oxidation state of Ni in this complex is 0. Ni is in 0 oxidation state. Similarly, FeCO5. Here also the complex have 0 charge, and CO have the 0 charge. CO is the ligands, and so that the summation of the charges must be 0. So X minus 0 is equal to 0. That is X is equal to 0. That is Fe having the 0 oxidation state in this complex. That is Fe is in 0 oxidation state.